Hi guys, welcome back to Foam Dude. Today we are going to continue from the point where we left the last time. We solved for heat conduction in the flange object that comes with the standard OpenFOAM tutorial. So today we are going to look at the basic case setup of OpenFOAM. If you're coming from a background with some work in commercial software packages, then you have probably used a nice user interface where it lists out all the options. You have all the buttons and all the knobs on the screen which you can control, you can modify to run your simulation. OpenFOAM offers you a more raw view of the CFD, where you have to interact with the software in the form of text files. Some people find it really hard to switch from a graphical user interface to the text-based user interface of OpenFOAM. So that's why I will try to make it as simple to understand and follow as I can. We are going to refer to the same flange tutorial that we did the last time. If you want to take a look at what's inside, just type in ls and it's going to show you all run, all clean, constant, zero, and system. So the names of the directories that are inside any of the case are always the same, regardless of what solver you use. So for any of your applications, your case directory should always have zero, constant, and system. The least. You may have more directories, you may have solution directories of time, but at the initial the initial condition when you execute your solver, the bare minimum requirement is to have zero, constant, and system. Zero, as the name suggests, it's your boundary conditions or initial conditions directory. You're going to specify boundary and initial conditions for all of the fields that you're going to solve for under the zero directory. Constant directory typically houses everything that remains constant in the duration of the simulation. It may have something such as the physical properties of your object, maybe thermal conductivity, viscosity of the fluid, and it also contains the mesh of your object. So everything that remains constant in the simulation duration should stay under constant directory. All the knobs, all the bells and whistles of the software or of your solver usually sit under the system directory. Typically, it's going to contain the numerical schemes, the solver details. It's also going to contain the details about how OpenFOAM interacts with your read-write operation. So let's start by taking a look at the zero directory. Let's look at what's inside zero, and you will see there is only one file called t. If you look at the solver, what we saw the last time is the solver Laplacian form solves for field t. So rightly so, in our simulation, you will only have boundary and initial conditions for field t. To see what's inside t, you're going to type in gedit 0 space t. If you're more familiar with Linux, feel free to use Nano or VI or Emacs or whichever editor you're more comfortable with. The boundary conditions are specified in a very typical structure that looks like what you see on the screen. You will have the OpenFOAM basic header on every single file that ships standard with OpenFOAM. This may look different if it comes from some third-party application. However, the specification of the boundaries should always look what you see here. You're going to see that the name of the object is t, and it comes under the class volume scalar field. The entity that we are solving for, the variable that we are solving for, the field is a scalar field. The dimensions are denoted here. Internal field, which is also your initial condition, is a uniform value of 273. So the entire object is initialized at 273 kelvins. The boundary field is the entry where you specify boundary conditions. As you can see, there are 4 patches in our object. Patch 1 is zero gradient, which means there is no heat flux through that boundary, or there is no heat flux passing across that boundary. Patch 2 is a fixed value type patch, which has value of 273. Patch 3 again is a zero gradient, which means there is no heat flux across that boundary. And patch 4 is a fixed value of 573 Kelvin. So this is how we can see the boundary conditions, and you can see it's a completely defined problem. Now let's understand what's in the constant folder. In the constant folder, you have a file called transport properties. So let's look at transport properties. Here you can see we are specifying value of dt of 4e minus 5 is the thermal diffusivity, and you can see it appears in the Laplacian of dtt. So we have to specify the value of dt, and we have specified the value as 4e minus 5. The object name is transport properties, and it's specified under constant. And you will see the same OpenFOAM header persisting in the transport properties file. Let's look at what's inside the system directory. In the system directory, you should always have control dict, FV schemes, and FV solution. Control dict is the controller of the simulation. It should have details about your time stepping, name of your solver, the format of your solution, precision, etc. FE schemes is the schemes for your solution, and FE solution is what solver it's going to use internally. So let's take a look at control dict. So you can see the name of the application is Laplacian foam. Start from is the time step where it should start from. So you can see the control is latest time. Alternately, you can have start time as the start control. So you could, instead of start time, you can, instead of latest time, you can specify something like start time. So it will always start from initial condition, which is 0. If you specify as latest time, it allows you to restart from the latest time step. The start time is specified as 0. Stop at is end time, so that is it's going to stop at end time. You can additionally make the solver stop at any given time by writing the control for abrupt stop of the simulation. The end time is the end time of the simulation, which we have specified as 3. Delta t is the time stepping. For steady state, it doesn't matter. For transient simulation, especially in this case, our solver is the transient solver. You have to specify the delta t. Write control is runtime, so it's going to write with respect to the runtime, and the write interval is 0.1 seconds. So you're going to have 0.1, 0.2, blah, blah, blah. Purge write 0, that means it's not going to delete any of the time steps written. For steady state solvers, it's rather critical to have purge write options specified as maybe 1, 2, or 3, which means that after every third time step, it deletes your time step, so you don't end up with a large number of results that you are not going to use. This is particularly critical for steady state, not so important for transient. The right format is ASCII. Additionally, you could have binary. It's a choice that you have. Write precision, you have 6 digits precision. Write compression is off. You can have on to have compressed results every single time. So it's going to create .gz files. Time format is general. Time precision is 6. And runtime modifiable is true. You could have false here. What this option does is, for instance, if you decide to change your dt, thermal diffusivity, midway in your simulation, keeping this true allows you to change your properties. If you keep it as false, then it will not allow you to change your, let's say, anything in transport properties. So I'm going to close this, and let's open FV schemes. In FV schemes, you see that the DDT scheme is Euler, the grad T scheme is linear, Gauss linear. In the Laplacian scheme, the Laplacian for DTT, it's Gauss linear corrected. Interpolation is linear, and the gradient schemes we are using corrected. For more details on FV schemes, feel free to refer to OpenFOAM user guide. Let's take a look at FV solution. Here you will see that for T, we are going to use PCG solver with preconditioner of DIC. Tolerance is the time step tolerance is 1e minus 0.6. Relative tolerance is the tolerance between, or rather, it's the change between the successive iterations. It's 0. If you specify this tolerance something like 0.1, you will see the simulation, uh, it terminates your iterations quickly or with a fewer iterations. It's better to have 0, so it forces the solver to solve to the tolerance of 1e minus 0.6. We will talk about this simple and number of non-orthogonal characters later in the later tutorials. So with given that, let's run our simulation one more time. I'm going to type in all run, and it's going to do something, and it's going to write out your results just like how it did the last time. So you can see, since our write control was to write out after every 0.1 seconds, you will see time steps are being written after every 0.1 second. If you look at constant now, you should see a folder called polymesh where your mesh sits. If you look at what's inside polymesh, you will see there is boundary. That's where you specify your boundary type. So let's look at what's the boundary type. We are going to open the boundary file. So you can see we have 4 patches and all are specified as patch. None of it is specified as wall. You can specify that as wall, but it's not so important in this case. If you have a fluid flow, then it's important to specify patches as wall, which allows you to specify more details such as wall functions, etc. So that is a complete overview of the basic construction of OpenFOAM. In summary, remember that you will always have a 0 folder, a constant folder, and a system folder, regardless of how you're going to mesh your object, regardless of what solver you're going to use, and regardless of what the overall system looks like. In 0 folder, you are going to have initial and boundary conditions. In constant folder, you're going to have things that don't typically change, such as the physical properties of your domain. And in system, you're going to have all the knobs and details of your solver. You're going to specify whether it's a steady state or unsteady state solver. You're going to specify your write controls and how OpenFOAM interacts with your read-write system. That's it for now. See you in the next one.